linear algebra student, this video is for chapter 5.1 part 2. Continue with finding eigenvector for a given eigenvalue. I'm going to do another example for a 2 by 2 matrix and then an example for a 3 by 3 matrix. In this particular one, lambda is equal to 4. We know that it is a eigenvalue. We want to find the eigenvector and actually the eigenspace. So that means what is the base that can span this eigenspace? Let's do the definition. So the definition that lambda is equal to 4 for A as an eigenvalue would be A minus A equal to AX equal to 4x, right? And that means A minus 4I times x is equal to 0 with a non-trivial solution. There's a non-trivial solution, and actually that solution is the eigenvector x, and we want to solve this. So that means I am to solve 4 minus I means 0, negative 2, negative 4, 2, minus 4, 0, 0, 4. So at the diagonal, I minus 4, because 4 is the eigenvector, times x is equal to 0. That means my new matrix would be negative 4, negative 2, negative 4. 2 minus 4 is negative 2 also, right? Just subtract 0 by 4, 2 by 4, because 4i is 4, 0, and that corresponds to ax equal to 4x. X is equal to 0. So that means I'm going to do the augmented matrix of negative 4, negative 2, negative 4, negative 2, 0, 0. And RREF become negative 4, negative 2. Let's go to the calculator. Do I have it? No. We can put it here. Negative 4, negative 2. You can do it by hand because negative 4, negative 2 actually would get rid of each other. It become REF of A would be 1, 1/2, 0, 0, 0, 0. So yeah, it's 1, 1/2, 0, 0, 0, 0. That means this x is x1, x2. x1 is equal to negative 1/2 of x2. x2 is free. So the free variable is this one. This is the previous position. So you can write the eigenspace as it's a set of vectors x2 and then negative 1/2, 1, right? So where x2 is real. And that means it is the span of what? Span of negative 1/2, 1. And if you want to use integer, or you can say span of negative 1, 2 multiplied by 2. So either way is fine. So this is the eigenspace for lambda equal to 4. Any vector of this form, multiples of negative 1/2, 1, would produce 4 times that vector after you transform it with A. That is the meaning of an eigenvector or eigenspace. Let's do it with a 3 by 3. So here we have lambda equal to 2. That means A minus 2i times x is equal to 0 to solve it, right? So now that we are more proficient with this, we'll just go to this right away. This means that ax is equal to 2x, and I would minus 2x on the other side, right? And 2x means 2ix, and I subtract this. So that means I actually just subtract it right away. Subtract 2 in the diagonal. Subtract 2, subtract 2, subtract 2. Do it here, so you can just do it in one shot. 0, 0, 0, 0. This is the augmented matrix. Negative 1. 3 minus 2 is 1. 1, 0. Negative 1, 1. 3 minus 2 is 1. Okay, augmented matrix, do RREF of it. Because we want to solve the x, right? This is the equation that we are trying to solve. It's a homogeneous equation, and we guarantee that there's non-trivial solution because it's an eigenvalue. So what was it? Oh, yeah, I have it here. Negative 1, 1, 1, 0, negative 1, 1, 1, 0, and 0, 0, 0. So REF of B give 1, negative 1, negative 1, 0, and then all 0. 1, negative 1, negative 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? So this is the private position. These two are free. X2 and X3 are free. So X1 equal to X1 equal to X2 plus X3. X2 is equal to X2. X3 is equal to X3. So if I'm going to write the eigenspace out, I can say this would become equal to X2 of 1, 1, 0 plus X3 of 1, 1, 0, right? So that means this whole thing is the span of, we can say, eigenspace for lambda equal to 2 is span of 1, 1, 0, comma, no, 1, 1, 0, 1. Yeah, there's a typo here. 1, 0, 1. Because x3 equal to 1 is here. There's no x3, so it's 1, 0, 1. Okay, so this is the eigenspace for a given lambda. Some theorem. Okay, so if no one tell me what lambda is, how can I find lambda? How can I find the eigenvalue of matrix A? So for some matrix, it's very easy to find, especially if it's a triangular matrix. So that means upper or lower triangular. If it is a triangular matrix, the eigenvalues are the entry on its main diagonal. So how come? Let's say we have 0 here, and then we have A11, A12, dot, right? A1n. No, A11, A22, ANN. For n times n matrix, and these are just something. So if it is so let's say an eigenvalue means minus lambda I x equal to 0 has non-trivial solution. So if a square matrix x equal to 0 has a non-trivial solution, that means this matrix, this is not invertible, right? By the inverse matrix theorem. If it only has a trivial solution, it would be invertible. But if you have a non-trivial solution, if you have any non-trivial solution, it must be non-invertible. Non-invertible, that means the determinant of these things, A11 minus lambda, A22 minus lambda, to ANN minus lambda, something 0, is equal to 0. So, and then we also know if you have a upper triangular matrix, the determinant is just the determinant of a triangular matrix is the determinant of the diagonal, right? So that means A11 minus lambda, A22 minus lambda, all of those multiplied together minus lambda is equal to 0. That means one of them has to be 0. That means AII is equal to lambda is an eigenvalue. You cannot have all of them not 0. One of them has to be 0. So the eigenvalues are entries on its diagonal. And actually, to solve this, so any one of them equal to lambda is an eigenvalue. So if someone gives you a upper triangular or lower triangular, so like this one is upper triangular matrix on the diagonal, and on the lower side of the diagonal is all 0. So what are all the lambda? Lambda is 1, 4, and -3, right? So it's very good. What about this one? This is an lower triangular matrix because these are all 0. So that means lambda is 9, 3, -3. Everything that is in the main diagonal. What about 0 being an eigenvalue? Now, 0 vector is not an eigenvector because A times 0 is always equal to 0 times that 0. But if I have, but 0 can be an eigenvalue. Okay, so how do I know 0 is an eigenvalue? So this is a, of course, it is a eigenvalue if and only if A is not invertible. So what is it if and only if? That means if A has an eigenvalue 0, then of course AX equal to 0x has some non-trivial solution. So that means A is not invertible, right? So it has non-trivial AX equal to 0 equal to 0 has non-trivial solution means this is by the inverse matrix theorem's converse. That means A is not invertible. The other way around, if it's A itself is not invertible, according to the inverse matrix theorem, AX equal to 0, X has non-trivial solution, so 0 is an eigenvector. So we know how to check if a matrix is not invertible. You can look at the determinant, right? So here, check if 0 is an eigenvalue. Yes, this is a lower triangular, upper triangular matrix, upper or lower triangular matrix, and the diagonal contain all the eigenvalue, and 0 is in it. So we know it is a, so 0 is a eigenvalue. Is an eigenvalue. What about this one? We know this is not invertible, right? A is not invertible. Why? Because there's a 0 entry, right? If you do RREF, you're not going to have an identity matrix. It's not reducible into identity matrix, so it's not invertible. So 0 must be an eigenvalue. At least you know some eigenvalue for a non-invertible matrix. So we have two cases. Either you have a upper or lower triangular value matrix, you can find eigenvalue, or if you had a non-invertible matrix, you know at least 0 is the eigenvalue. And also we can also use some properties of an eigenvector to actually find value of a square x or a to the kx, right? So let's say if I know x is an eigenvector, so if I do a square x, that means I have a times x. Matrix multiplication is associative, so I can do this first. So be a times lambda x. Right, lambda is a scalar, so I can move it. So I can move it in the front as a constant, lambda ax, and it will be lambda x. Right, because ax is lambda x. That means lambda square x. So if you are to find a transformation of for x 2 times, it's the same. So if x is an eigenvector, then it will be lambda square x. Some of the properties of eigenvector. This theorem say that if V1 to VR are eigenvector, that corresponds to different eigenvalues, then the set V1 to VR is linear independence. Okay, so you have all different eigenvectors, then you have linear independent vectors. So proof, let's say, just assume contradictory. V1 to Vp are linear independent. But the next one is not. But not Vp plus 1.